Okay, so before tackling this problem, I think it's worth first looking at the solution to a slightly simpler problem. So this is pseudocode for generating all possible subsets of a given set of n elements. So in other words, the power set of a given set S. So we're taking as input a set containing n elements, and we're going to use decrease and conquer to generate all subsets. So it's a recursive algorithm. So first we test for base case. The base case here is that we've been given a set containing 0 elements. In that case, the only subset is the empty set, and so the set of all subsets is just the set containing the empty set. Okay, so that's the base case. Right, now for the recursive case. So here's the decrease and conquer part. So the first thing we're going to do is make a recursive call with just the first n-1 elements. So this is the decrease and conquer part of the algorithm. So we're going to get, in other words, all subsets of S that do not contain element n, so En. Alright, now the second part of it is to generate all subsets of S that do contain the last element En. And the way we do that is we just go through all elements that don't contain En and add En to them. So that's what we're doing here. Okay, and the last thing we do is just return the union of these two. Okay, so just to sum up, we're given a set of n elements. If n is 0, we just return the set containing the empty set. There are no other subsets. Otherwise, we first generate all subsets of the input set that do not contain the last element, En. Then we go through that set and add En to it. So now we have all subsets that do contain En. And the last thing we do is return the union of those two. Okay, so now let's get on to the question that we've actually been asked. Okay, so what we're asked this time is to generate all combinations of k items from a given set of n items. So in other words, all k element subsets of a given n element set. And we're going to take a similar approach. Okay, so let's call this function combinations, and it's going to take now two inputs, k, the size of subset that we want, and S, our set of elements. And what we need to do is return all k element subsets of S. So let's think about base cases. So it's not totally obvious what base cases you might use here. You might think to use the same one as we did in the last example, and that would be when S is empty. You definitely could use that as a base case, and it wouldn't break anything, but actually we don't need it. So if we think about it, we can make some immediate decisions about what to return if, first of all, k is 0. So now we're being asked for all subsets of S that are of size 0. And there is one such set. It's the empty set. So we're going to return the set containing the empty set, and that is the set of all subsets of S that are of size k, but k is 0, so there's only one subset. So it's the empty set. Okay, there's another base case, which is that if we're being asked to return subsets of size k, and that is larger than the size of the set S, then there are no subsets. So now we just return the empty set. So the set of all subsets of size k of S, there are no subsets, so that set is empty. Okay, those are our two base cases. Now for the recursive case, we will take a similar strategy to what we did before. So let's just say E is any member of S. It doesn't matter which element we choose, it's just one element. Okay, and then we're going to make a recursive call and we're going to compute a set. I'm going to call it S out. And this is all subsets of size k of the set S with the element E removed. So in other words, this is forming part of our solution. These are all k element subsets of S. They just happen to not contain the last element or the element that we chose, E. Okay, so that's one of the reduce and conquer calls. Now, the other part of it is we also need all subsets of S of size k that do contain element E. But this time we can't reuse S out because if we add E to it, they're going to be too big. So it's obviously going to include a recursive call in which we reduce k by 1. So somewhere we're going to have a call that looks like combinations k minus 1 S minus E. And then we would just need to add E to all of those sets. So let's just move this a moment. Alright, so let's think how we can write this down. So S in is going to be the set of elements from this recursive call, I'll call them C, unioned with the set containing this element E, where C is a member of this. Okay. So let's just repeat what this means. So S in is going to be the set of all subsets of S of size k, and I'm going to construct them by adding this element E to these other sets C that come from the recursive call where I asked for all subsets of S minus E of size k minus 1. Okay, and then the last thing I do is I return the union of S out and S in. One interesting thing, if you go and implement this in Python, you can do it such that your code looks almost identical to my pseudocode here. So you can write the construction for S in, you can write using a list comprehension in Python. You can use lists to represent the two sets because they never have shared elements, so when you do the union you can just concatenate the two lists.